right, guys, so we're going to be talking about ionic bonding for the next couple weeks. We're going to also include naming and writing, but that won't be till after Christmas break. Remember, the semester extends 2 weeks after Christmas break due to the fact of our late start. So we're going to continue with this chapter after break, so there won't be a test that you're going to have before you leave. There'll be some quizzes, but there won't be a test. So what we're going to be talking about here for ionic and metallic bonding is we're going to be talking a little bit about the Lewis dot structures that we talked about in the last chapter. So electron dot structures are diagrams that show valence electrons, okay? So remember in the last chapter, when you were looking at valence electrons, it was by column. So group 1, column 1 is 1 valence electron. Group 2 is 2 valence electrons. The middle section, remember, those are transition metals, so they're going to all have 2. And then once you get to column 13, it becomes 3, then 14 is 4, 15 is 5, 16 is 6, 17 is 7, and 18 is 8. Remember, you can only have a maximum of 8 outer electrons, okay? And this Lewis dot structure is going to be very important when we talk about formation of cations and anions, okay? Now, when we're looking at the octet rule, octet means 8. So everyone is trying to get to 8 on the periodic table, metals and nonmetals. Metals will lose their valence electrons, leaving a complete octet in the next lowest energy level. Nonmetals, because they're closer to the noble gases and have more outer electrons, will tend to gain electrons or share electrons with another nonmetal to achieve a complete octet. The most common cations, and when I say a cation, I'm talking about metal atoms, okay? And so when the most common cations are those produced by the loss of valence electrons. So they're giving their electrons away, their outer shell electrons, and becoming positively charged. Normally that's a metal atom because usually your metals have lower valence electrons than your nonmetals. Nonmetals are closer to the noble gas column. So you can represent the electron loss, or what we call ionization, of the sodium atom by drawing the complete electron configuration of the atom and the ion formed. So, as you can see, what happens here is you have your electron configuration and that outermost electron. So sodium has 1 valence electron. When sodium loses that valence electron, it becomes a sodium ion. When that happens, it now takes on the same electron configuration as a noble gas, meaning it's inert. It doesn't react with anything. They actually use sodium ions in the street lights in the city of Little Rock. Mostly all of your cities will have these street light lamps that glow yellow, and that's because down inside underneath the ground they have these pipes that lead up to the lamp post, and it's actually sodium ion gas, and so it's illuminated. So therefore the cities don't have to buy light bulbs and sit there and replace light bulbs. It would be very costly to do that. So because when you put sodium in ionic form, it doesn't now react with anything, you can use it in different situations that you wouldn't be able to before. So what's happening is, in order for these metals to gain stability, they're going to have to lose valence electrons. So this is actually what's happening in a valence electron. You have your Lewis dot structure, so you have sodium, and it's got this dot, okay, 1 dot, 1 valence electron for the Lewis dot structure, and it's going to lose that valence electron. When that happens, we now have, so when you started out with the neutral atom, you had 11 protons and 11 electrons. Now when you lose that electron, you have 11 protons but 10 electrons. So you have 1 more proton now on your nucleus than you do electrons around the nucleus, therefore making this positively charged. And your electron is going to go out and try to find a non-metal that's looking for an electron, okay? So here's what's actually happening with the transfer of electrons. So sodium, okay, is going to transfer that electron, lose it, okay, move it out, and then you're going to be left with a sodium ion. Notice the size. You're losing an electron, so that outer energy level shrinks down because now you have the configuration of a noble gas. It's still sodium, so it still has properties of sodium, However, it does change a little bit in its structure and how it reacts. Now, what if we had magnesium? Magnesium is in group 2, so it has 2 valence electrons. So when these metals try to achieve stability, they're going to lose all of their valence electrons. So magnesium has 2 valence electrons, so it's going to lose both of its electrons, and it's going to become a positive 2, meaning that it has 2 less electrons than it does protons, okay? Those electrons are going to go and find a nonmetal. Now, as you can see, we've been talking about this in the last chapter, how elements have similar chemical and physical properties by column, by group, right? So if you look here, okay, the first column, or group 1, will all have 1 valence electron. They will all lose 1 valence electron, becoming a positive charge. All of group 2 will lose 2 valence electrons and become a positive 2. Now, column 13 is a little bit tricky because some of them in column 13 are metals and some are not. So you can't go by the whole column. And then 14 is the same way. Because of your metalloids, it doesn't follow that same trend, okay? Now, anions are when you have nonmetals and they're closer to the noble gases. So in an anion, the gaining of negatively charged electrons by a neutral atom gaining an anion, okay? It produces an anion. So it's going to gain enough electrons to make 8. So it wants 8 outer electrons, just like the metals do. But the metals, because they have limited valence electrons, it's easier for them to lose 1, 2, or 3 electrons than it is for them to gain 5, 6, 7, or 8 electrons, okay? So the idea behind this is metals will lose and go down a row in order to gain stability. Nonmetals will gain enough electrons to move over to gain stability. So what happens here is an anion is an atom or a group of atoms with a negative charge. Why do they have a negative charge? Well, because what happens is, now it's like the reverse effect. When you have, say for example, chlorine, which has 7 valence electrons, okay? Actually it has 17 total electrons. So what happens is when chlorine gains 1 more electron, it moves over, okay, and becomes argon, which is 18, okay? Now, when it does that, it still has 17 protons. So now it has 1 more electron than it does protons. So that's where the negative charge comes into play, because electrons carry a negative charge. Now, when you gain this electron and become negatively charged, the name of the atom actually changes. So chlorine becomes chloride. Fluorine becomes fluoride. Have you ever gone to the dentist where they painted that fluoride on your teeth? Well, it's important to know they're painting fluoride, not fluorine. And the difference is fluoride gains 1 more electron and now has the same configuration of neon. And the reason that's important to know is when they put that on your teeth, if it was fluorine, it would react with things around it. Okay, so when you would eat stuff, eat food, it would actually react with food in your mouth. So when you have that fluoride, you've now gained enough stability where you have a full outer shell. So the fluoride's not going to gain electrons and bond with anything, okay? So it actually protects your teeth and then prevents anything else from reacting on your teeth with the fluoride, okay? And that's also, while some compounds will actually break down the enamel on your teeth, fluoride does a protective layer on your teeth when they paint that on there, so that's why the enamel doesn't break down. So it's kind of interesting to see how 1 electron, when you add that 1 electron, it's going to change the properties of fluorine, make it fluoride, and then we actually use it to help prevent tooth decay. Now here's what's happening when a nonmetal gains an electron. So see, you have chlorine, which has 7 valence electrons. So it's going to gain that electron and now have 8 and become negatively charged, okay? So here's what's actually happening. Now, chlorine is smaller in size, but now it's going to gain that electron. Look how much larger it gets, okay, in size. That 1 electron makes a huge difference in the size of the chlorine atom, okay? So positive and negative ions form when electrons are transferred between atoms. Now, the ions that are produced when atoms of group 17, so group 17 are called the halogens, okay? When these elements gain electrons, they are now referred to as halide ions, Okay, so all halogen atoms have 7 valence electrons. All halogen atoms need to gain only 1 electron to achieve the electron configuration of a noble gas. Now, same thing before, by column, okay, so column 15, they have 5 valence electrons. So they only need 3 to make 8. So they're going to form a -3 charge. Group 6 is, or 6A is 16. It has 6 valence electrons. So it only needs 2 to make 8. So it's going to gain 2 electrons. So the column of group 16 is going to be -2. And then finally you have group 17, which are your halogens. They have 7 valence electrons. So that group is going to gain 1 electron to become stable. All right, so I'm going to send out another video later which will help you understand the formation of cations and anions, okay? I'm going to draw them out for you on paper because it'll be a little easier for you to see versus me doing it on the board. You're going to have this paper on formation of cations and anions, and so I'm going to kind of show you how I want you to do that. All right, so I hope you guys have a great day. Take care.